हाय फ्रेंड्स, पढ़िए विद प्राची में आपका स्वागत है। आज है मेरा डे 1 लेसन 1 क्लास 10th मैथ्स चैप्टर 1 रियल नंबर्स। चलिए शुरू करते हैं। हेलो स्टूडेंट्स, हेलो फ्रेंड्स, पढ़िए विद प्राची में आपका स्वागत है। ओके, सो आज है लेसन 1 चैप्टर 1 ऑफ मैथ्स क्लास 10th CBSE real numbers. You have already learned this, some part of this in class 9th, and we are going to expand on this topic as it's taught in our NCERT textbook. So let's go. So what I've presented here is the whole gamut of real numbers, right? So first is natural numbers, which are the numbers which we use in our day-to-day lives. 1, 2, 3, 4, 5 up till infinity. Next is whole numbers, which also includes 0 here. Then we have integers, which includes negative numbers, 0, and these positive natural numbers. We have rational numbers, which include integers, which includes fractions, terminating or repeating decimals. So if we go by an example, 3 by 2, it's a fraction. It's a terminating decimal, 1.5. 1 by 3 is a non-terminating, it's not a terminating decimal. So 1 by 3 is an example of repeating decimal, where it goes up till 0.33333. So we can represent 0.3 with a bar here, like I've mentioned here. Next is irrational numbers. These are non-terminating and non-repeating decimals. So they cannot be, so you had learned this in class 9, that they cannot be written in the fractional form of p by q, where p and q are integers and q is not equal to 0. See, some examples are the square root of 2, 3, 5 and pi. Pi is what? 22 by 7. If you expand this, it keeps on going at 3.14, 2, 8 up till infinity. So this is just a recap of the whole numbers, and now we'll proceed to our textbook. So we are going to start with theorem 1.1, which is specified in our textbooks. I've specified it here as well. It's a fundamental theorem of arithmetic, and it has many real world applications, which we can discuss later on. As of now, the theorem states every composite number can be expressed, factorized as a product of primes. And this factorization is unique apart from the order in which these prime factors occur. So if, for example, what we are trying to say is that if any number n, it has these as the prime factors p1, p2, p3, pn. So these are all unique prime numbers, and these factors are all unique. So these are known as the factors of this number. They are all unique, right? It's a product of primes, any composite number. So any composite number can be specified as a product of primes, where this factorization is unique apart from the order in which prime factors occur. So I'll explain what does this mean exactly. So let's take an example from the textbook itself. Okay, so we can go to exercise 1.1, and I'm just taking an example here so that we solve the exercise as well as I am sort of helping you understand. So the number is 140, right? You know this. We already have done this in our previous classes, LCM, HCF and all of that. So we can start with the lowest prime, which is 2. We know it's 2 into 70. 2 into 2 into 35. If we break up 70 into this, then 2 into 2 into 35 is what? 5 into 7. So how can we express 140 as 2 square into 5 and 7? So what does this theorem say? Fundamental theorem of arithmetic. Every composite numbers can be expressed as a product of prime, where such factorization are unique. So this is unique, 2, 5, 7. except for the order in which they occur. You can write this very well as 7 into 5 into 2 to the power 2, right? That does not matter. This does not matter. 5 into 7 into 2 to the power 2, right? This does not matter. What matters, and by the main point, is that this is unique, right? So what we usually do is that we write it in ascending order. So I've straight away explained to you with the help of an example, right? We can then jump on to the questions and we will solve each of them now. So again, what is fundamental theorem of arithmetic? It states that every composite numbers can be expressed, when we say expressed, we mean factorized, as a product of primes, and this factorization is unique apart from the order in which these prime numbers occur. So this is the fundamental theorem of arithmetic. So now we are going to go to the exercises. So the first question is 3825. We can obviously see by the number 5 that it's divisible by 5. It's not divisible by 2. It could be divisible by 3. We can check whether it is or not. 12, 15. Yes, it is. How do I know? 3 plus 8 plus 2 plus 5, which is 3 plus 8 is 8 plus 2 is 10. 10 plus 5 is 15. 15 plus 3 is 18. 18 is divisible by 3. So hence this number is divisible by 3. How do we know when the number is divisible by 3? When the sum of the digits is divisible by 3. So 3 is definitely one of the numbers. So if I write it, it says 1, 2, 7, 5. This is again a number which is divisible by 3. So because 1275 is again divisible by 3. So 3 square into 1, if 1275 was a number, 425. Now it's not divisible by 3. So how do we specify this? 5, 85. Now what is 85? So again, what is it? A composite number can be specified as a product of prime, where this factorization is unique. So these factors are unique. So this is what we have to specify over here, right? So another example, can straight away say that it's 5 into 1001. So this is 5 into 11 into 91. And what is 91? 5 into 11 into 17 threes or 13 sevens, I think. 7 into 13, I think. 7 threes are 21, yeah. So here you can see the order is specified as 5, 11, 7 and 13. Usually, preferably, we specify it as 5 into 7 into 11 into 13. We specify it in the ascending order. Understood? So this is how we specify as a product of primes, and this, I think we have learned this previously in our previous classes as well. I have not taught, but you would have learned in your school. Coming to the next exercise. In this exercise, we are supposed to find out the LCM and HCF of these numbers. We know for a fact that this is 26 is 2 into 13. So what we are doing first is we are expressing it as the prime factors, product of the primes, and 91 is 7 into 13, right? So what is the HCF? Highest common factor, 13. And what is the LCM? So what is the LCM? 2 into 7 into 13, right? You can multiply and find out what it is, but this is the number. Similarly, now the next question, 336 and 54, we'll first express it as a product of its prime. So probably I should show this in more detail. That's the numbers were 336 and 54. I'll again show as how my mind works, how it is. 6 is there, right? So it is obviously divisible by 2. It could even be divisible by 4, but we'll figure that along the way. Since the numbers 3, 3, 6, they are divisible by 3, it's divisible by 3, right? Either, how do you know? You can add them up, or you can just in your mind sort of calculate. See, this is something which I know, I'm sure you would have been taught in your previous classes. So that's how you do it. So 2 into, so when I do, so 2 I know that definitely is there. 1, 2 ones are 1, 1 3 is at 6. I don't know why I'm going to the basics, but here I am. Okay, 1, 1, 3, 6, 1, 6, 8. So 2 square into 84. So it definitely seems to be that it might go till 2 to the power 5 also, but we'll figure out. No, it will not go till 2. It will go till 2 to the power 4, I think. 16. What is 2 to the power 4? 16. 2 into 2 into 2. 16 into how? It's 16 into 21, right? 16 into 21. So 2 to the power 4 into 3 into 7. So these are the factors here. 54 we know is 6 into 9. So we can just mention here 54 is what? It is 6 into 9, right? So it's 2 into 3 square. I think 3 cube actually. 2 into 3 cube. So now LCM and HCF. HCF would be the common digits here. So we have 2, 3. So 2 into 3. And HCF would be the common digits, common factors. And LCM would be the highest number. So when we look at 2, we will consider the highest one, 2 into power 4. Then 3, this is 3 here, 3 cube here, so we'll consider 3 cube. And then into 7. You can multiply this. We can multiply it for you. 16 into 27 into 7, right? So we can do that. So it's 3024. We can check whether it's the same or not, and HCF is this. So this is the answer for this. LCM is 3024 and HCF is 6. We'll go to this question. See already in this question where we are asking for the LCM and HCF for them, it is already, so when we are asking for the LCM and HCF, these are already primes. These three all are prime numbers. So LCM obviously will be the product of these. And HCF would be 1. Done here is, I've again sort of thought I'll again take you through more examples. So these are the exercise questions that I have specified here. And there's one more concept in a 2 digits when there are 2 composite numbers, the product of the LCM and HCF. So LCM into HCF is equal to product of the numbers. Right? So we'll look at that. No, it's 5 into 7. 35 is a 3 2s are 6. 2 5 7 65. That means 5 square into 1 163 5, right? So 5 square 5 cube into 27. And what is 27? We know is 5 cube into 3 cube. So this concept was left, right? This concept was left in the exercise that we were doing. So 510 and 92, these are the factors, how I have taken out, right? So these are the factors. So what would the LCM be? So LCM would be, so we will consider each of the factors and the highest number here. So 2 square is the highest number, 2 square, 3, 5, 17 and 23. So this is the LCM, and HCF would be the 2 is the HCF. So if we multiply this, 4 and 3, 12, 12 5s are 60, 60 into 17 into 23, let's just multiply this, 6 7s are 42, 1020 into 23, 23 2s are 46, I think, let me just do it properly, 3 2s are 6, 23, 2 2s are 4. So yeah, so the LCM is 23460, right? So now if we take the next concept is that the product of the numbers, two numbers, the product of the two numbers is equal to HCF into LCM. So if we take HCF into LCM, right, so we have to multiply these two numbers. Sorry, it's all going haywire right now. No worries. So 2 6s are 12, 2 4s are 8, 2 3s are 6, 2 2s are 4. So the product is this. Now if you consider, hopefully this comes right? So 92, 51, 92, 5 to the 10, 46. Right? So it's 46920. Here the number is 46820. So I'm sure there's some mistake in this. 2 2s are 12, 2 4s are 8, 9. So this is coming correct. So this is what I've done is I've actually multiplied and shown. But if we just look at these numbers, how is 510 shown as this? How is 92 shown as this? What is the product if we take the product, right? So product will have 2 cube, right? If we look here also, this and this form 2 cube, and rest the numbers are there, 3, 5, 17, 23, 3, 5, 17, 23. So even without the calculation, this is proving to be correct, but we have shown you with the calculation. So one of the question here is, consider the number 4 to the power n, where n is a natural number. Check whether there is any value of n for which 4 to the power n ends with the digit 0. So 4 to the power n, right? So 4, how can 4 be expressed as? 2 to the power 2 to the power n. That means it's 2. Now for it to end in 0, there definitely has to be a 5 here, right? Because 5 into 2 is 10. So that there itself we get our answer, that it cannot end in 0, right? We have another question in the book also, which says that check whether 6 to the power n can end with the digit 0. So again, same, 6 to the power n is 2 into 3 to the power n. There is no 5 here, so it cannot end at 0. Now there are 2 more questions which I would like to do in this exercise 1.1. Okay, so the question is whether this is a composite number or not, right? So what do we mean by composite number? Composite number can be expressed as a product of prime numbers, right? So what will we do here? We'll simply multiply this. 77 into 11, 77, 77 13s are 13 7s are is what? 91, right? 19. 13 7s are 91, 91 900. So 1001 plus 13, which is 1014. Now what is 1014? 2 into 507, 2 into 3 into 3, 2 0 is 6, 2 7 is 9, so 2 into 3 into 13 square. So yes, this can be expressed as a composite number. The next question is, there's a circular path around a sports field. Sonia takes 18 minutes and Ravi takes 12 minutes for the same. So if both of them start at the same time and same point at the same time and in the same direction, after how many minutes will they meet again? It will be the LCM, right? 18 and 12. So LCM of 18 and 12. So we'll find 18. What is 18? 6 into 3, which is what? 2 into 3 square. And what is this? 2 square into 3. And what is the LCM? 2 square into 3 square, which is 36. So they will take 36 minutes to meet. If you want to understand by a simple example, we can just consider 2 numbers, 2 and 3, right? If this is a circle, so for example, I take 2 minutes, someone else takes 3 minutes. So when that someone else is completing 3 minutes, then I'll be that much more ahead, right? So we have to find at the point at which this person will catch up to me and we both will meet at this point. So it will be 6 minutes. In 6 minutes, I would have completed 3 rounds and the other person would have completed 2 rounds. And we'll meet at the same point. So friends, that's the exercise 1.1 completed of chapter 1, real numbers of class 10 maths CBSE NCERT textbook. We are going to proceed to exercise 1.2 in our next class. Till then, like, share, comment and subscribe to my YouTube channel.